Here we come to DSE Physics 2018 question 4. Here we have a spring gun loaded with a cannonball, the spring being compressed, and so elastical potential energy is stored. And when the spring is released, when the gun is fired, the ball will be ejected with a speed of 4 meters per second, so it has Ke. And when you compare between this figure and this figure, you'll find that the cannonball is at a higher level. Okay, so the difference in height is 0.2 meters. So at the same time, it has Pe. So basically what happens here is the elastical potential energy is changed into Ke plus the Pe. So let me write this down. So originally we have EPE. We do not have Ke. We do not have Pe. However, later on, the spring is released. No longer we have EPE, but we have Ke and we have GPE. So this is a conversion of energy. By considering the conservation of energy, we know that the EPE stored in the spring is converted to the Ke of the ball and the GPE of the ball. So in part A1, it is asked us to calculate how much energy transfer from the spring to the cannonball. So basically we are calculating the amount of EPE in the spring. So we can express the Ke in terms of half mv squared and the GPE in terms of mgh. So as the cannonball is moving with 4 meters per second, we can substitute in the number. Mass of the cannonball is 0.3 kg. And the height would be 0.2 meters. And this gives us 2.9886 joule. So this is amount of EPE stored in the spring, and therefore this amount of energy will transfer to the cannonball when it is released. Part 2. Explain whether the total momentum of the spring gun and the cannonball is conserved. We know that if there is external force acting on the system, momentum will not be conserved. Momentum is conserved only when there is no external force. So when you look at this system, you ask yourself a question: is there any external force? Now, if in case the spring gun and the cannonball is an isolated system, that means it does not react with the environment. This is an isolated system. Then there will be no external force. However, is this really the case? We can see that this spring gun is fixed to the surroundings. It is fixed, or else it cannot fire a cannonball. So let's say this cannonball is fixed to the ground. So we can fix it to the ground. So it does not move at all. No matter before it is fired or after it is fired, the spring gun do not move. It is fixed. So when the cannonball is being fired, we know that the gun should coil backwards. But why didn't it move? Because the ground would have a supporting force that acts on the spring gun. So basically, this is not an isolated system. Or in other words, yes, there is external force acting on the spring gun. Like in that case, if there is external force acting on the spring gun, the total momentum is not conserved, as there is external force acting on the system. Okay, you can think about this in another way. At first, in this situation, the momentum is zero because nothing is moving. But in the second case, the cannonball is moving, so the momentum of the whole system is larger than zero. So there is a change in momentum. So momentum is not conserved. Part B. So now we have a spring cannonball flying. It's projected at 50 degrees to the horizontal initially. Don't forget that the speed, we had already calculated the speed. We had not, had we calculated, the speed is given. The speed of the cannonball is 4 meters per second. So let's write it down here. U is equals to 4. So now we want to calculate the range R and the time of flight of the cannonball to a point that is horizontally away from the original position. So that means now the starting point and landing point is on the same level. So we are talking about the special case. So we can apply the formula for special case. Okay, so if you do not want to apply the formula, we can calculate it in our way. So how to calculate the range? The range means this distance. So this is R. And also we want to calculate the time of flight, that is the time when the ball reached this point. Okay, so firstly, what do we know about it is, firstly, when it returns to the same level, we know that Sy is equals to 0 when it returns to the same level. So Sy is equal to 0. So we can focus at the vertical motion. First of all, let us resolve the velocity into its horizontal part, 4 cosine 50, and its vertical part, 4 sine 50. Okay, we focus on the vertical part of the motion. Sy equals uyt plus half ayt squared. Sy is 0. Uy is 4 sine 50. Ay is negative 9.81 t squared. Oh, sorry, we do not have t, so we cannot use this equations of motion, but we can we actually can find t first. So here we have a quadratic equation. After we solve the quadratic equation, we know that t is equals to 0.6247 meter per second. Now once we have the time of flight, then we can consider the horizontal motion and then find the range. The range means the horizontal displacement. And because horizontal motion is a uniform motion, we can calculate using S equals ut. So ux is equal to 4 cosine 50 times the time of flight 0.6247. So the range is 1.61 meter. Part C. If the projection angle is increased slightly greater than 50 degree, originally is 50 degree, now it's greater than 50 degree, initial speed remains unchanged. Without any calculation whether there's any change in TF. Now if originally it is at 50 degree and then it changed to slightly larger than 50 degree, let's say 51 degree. Now in that case you can expect that there is a larger component of Uy and a smaller component of Ux. Okay, Uy will be larger, Ux will be smaller because it's pointing upwards a little bit. What does the time of flight depends on? Does it depend on Uy on Ux? Remember the time of flight when it goes up and down again, when it goes back to the original. Actually, it only depends on the vertical motion. Okay, so it depends on the vertical motion. Now, the upward velocity is higher. So we expect the time of flight will also be higher because it takes longer time for it to come back to the original position. So we do not need any calculation. We just know that horizontal motion and vertical motion are independent to each other. The time of flight depends on the vertical motion. Both the initial vertical component of the velocity increases. The time of flight of the ball would also increases.